bars won't get destroyed over time. On the other hand, the cheap brass nuts might have to be replaced after several hours of operation. If your soldering iron hasn't enough power to heat up the metal stripe, you can use a candle. As you can see, there is some clearance when using just one nut for the drive. The second metal stripe is mounted in such a way that the clearance is as low as possible. The lower the clearance, the higher the friction. The right adjustment is a compromise between friction and clearance. The axes are guided by the middle aluminum bar using perforated metal stripes as well as 3mm screws and nuts. Once again I am using brass nuts at the ends of the screws to reduce abrasion of the aluminum angles. Same as with the threaded bars, the adjustment is a compromise between low clearance and friction. The mechanism for the Y-axis is built in the same way. Both axes can process linear movement. The sensor disc for the rotary encoder is cut from a tin can. That's what all scissors or metal shears are good for, the center hole is made without a drill. The axes are driven by standard servos having metal gears and ball bearings. Two of the servos have to be modified for continuous rotation. First, the stopper on the gear at the output shaft has to be grinded. After that, the potentiometer has to be removed and replaced by a voltage divider composed of two constant resistors. The advantage of this type of servo is the 3mm thread at the output shaft. The threaded bar for the drive can be mounted easily on the output shaft of the servo, use a nut to fix the drive. The rotational encoder is scanned by two photosensors. The state of the sensors is read by the Arduino Uno. The third axis is moved by a normal servo. The Arduino is mounted at the backside of the CNC machine. There is a 12V relay used to switch the router. The relay is controlled by the Arduino through a small signal transistor. An old computer power supply feeds the machine with electricity. Time for a first test run. I am using a pencil to plot an L. The machine runs fine, but it is very slow. For the tiny L being just 8mm high, the machine needed 2 minutes and 39 seconds. Time for a second servo hack. The gear ratio has to be lowered. A simple way is to remove two gear wheels. In doing so, the gear ratio is reduced from 1 to 260 to just 1 to 13. However, with that ratio, the torque is too low to move the axis. When removing just one of the gear wheels, the motor has to be mounted on a new position. The case of the servo has to be cut to bring the motor close enough to the first gear wheel. I have used hot glue, but you can also use some epoxy. The servos I am using are not very reliable, one broke while recording this video. The weak point are the brushes inside the motor. At the broken motor, the brushes deformed in such a way that the terminals were shortened by what the servo board smoked up. I have opened the motor and cut new, more solid brushes from a tin can. The new board is from another standard servo I had in stock. After opening the second servo, I saw that the brushes of that motor were also in a very bad condition. I used some solder to stabilize the ends of the brushes, by what this servo still runs fine. With the reduced gear ratio, the L is plotted in less than 50 seconds. The software on the host computer runs with Linux from the command line. With that program you can choose a file and set some parameters. Let's plot a test pattern with a ball pen on a piece of paper. The software processes scalable vector graphics with all paths turned into line segments. The test pattern consists of some concentric circles and 4 lines arranged with an angle of 45 degrees between two paths. The plot is compared with that pattern printed on a foil using an inkjet printer. There are noticeable deviations, but considering the simple construction, the result is not too bad. The maximum speed is just around 1mm per second, you need patience when working with that machine. When moving the pen to one point from both directions, you can determine how precisely you have adjusted the drive. The error is just a minor fraction of a millimeter, not so bad for that cheap machine. Next I am engraving glass, thus the router has to be mounted on the vertical axis. The diamond milling cutter has to be cooled with some water during engraving work. Even with the modified servos, the CNC machine needs approximately 60 minutes to process the file. The result is really good. In plotting mode there is almost no side load on the ball pen, but the router has to be pulled with higher force over the glass plate during engraving work. As you can see, the aluminum bars as well as the iron angles are deformed under load. The threaded bars are also a source of inaccurateness. The end of the X drive shown here starts vibrating at a certain speed and position. An additional guide will limit the amplitude of those bad vibrations. You always have to be aware of resonance vibrations when using a CNC machine. If the router moves with a certain speed and downforce along the glass plate, the mechanism starts vibrating vertically. Avoid that operating mode by choosing appropriate machine parameters. When lowering the vertical axis, there is inevitably also a movement along the X-axis and the router tilts slightly. Both causes an oval-shaped drill hole in theory. In practice, that movement is negligible. To the left you can see the hole drilled with a CNC machine, the hole to the right was done with a drill press using the same 3mm drill bit. The CNC machine is not free from clearance, thus the hole is not as smooth as it ideally should be, but it's not oval. Next I was cutting gear wheels from 2mm acrylic plastic. The result was disappointing. The poor quality was mainly caused by deflections along the vertical axis of the mechanism. For CNC machines there is. Solid isn't always solid enough. After enforcing the machine and changing the mechanism used to lift and lower the router, I started a second run. Always cool the drill bit to avoid the plastic from melting. The software computes special gears with round teeth. The parameters needed are the number and the diameter of the gear teeth, the diameter of the central hole as well as the diameter of the drill bit. The second run with the enforced machine was much better. The teeth at the start and end point of the cutting process are clearly deformed. The gear breaks from the blade before the router has reached the final position. You get a better result when cutting the gear in 2 or 3 runs. the router is lowered to just half the thickness of the plastic in the first run. The router cuts through the plate in the last run. Use a file to finish the gear wheel. The quality of the parts is sufficient to build a gear train. The router can cut 1mm plywood more easily, thus you can higher the speed of the machine slightly. The parts of the puzzle are mirror inverted because the edges at the bottom of the plywood are cut smoother than those at the top of the plate. Approximately 1 hour is needed to cut all parts of the puzzle. This is not a speed record breaking CNC machine. When the machine has finished its work, the edges have to be smoothened with sandpaper. Put raw material in and get perfect parts out is nothing you get with cheap machines. With some paint and glue, we get a well-known bird. It's hardly recommended to rethink your software strategy if you don't know the name of that penguin. You can also engrave wood. Here I am engraving 20mm chipboard as used for the frame of the machine. The mechanism of the CNC isn't ideally plane and the drive doesn't move ideally in parallel to the base plate. As a result, the router is diving into the material with varying depth when moving along a path. You must have a close look at the blade to notice that error. You can lower the router for a second run. Leave all other parameters of the software unchanged. The paths are clearly visible now. The cutting edge isn't perfectly smooth, thus you can't engrave tiny structures with this machine. The characters shown here are approximately 5cm high. What about more solid materials? Here I am cutting a 1mm aluminum plate. For this machine, aluminum is heavy metal. The mechanism is bent clearly, as you can see and hear, the router vibrates sometimes hardly while cutting the material. Mainly the movement along the vertical axis causes improper cutting lines. The result is eventually acceptable, but definitely not very good. The 3mm plate of Debron processed here can be cut very easily. The material isn't cut with a router but by using a soldering iron with a 1mm copper wire at its tip. Consequently, processing Debron with that CNC machine is more quietly. The length of the copper wire should be chosen in such a way that the temperature is just enough to melt the Debron. That reduces the bad smell of evaporating plastics. The width of the cutting line is approximately 2mm and there is almost no side load on the tip of the soldering iron. Debron is cheaply available and it is a proper material to demonstrate how a CNC machine works. The machine is meant to be an educational tool for learning how to do computer numerical control, it's not a productional tool. You have to go to the starting point manually, and there are no switches detecting the endpoints of movement. You can adjust many software parameters by what many things might go wrong. If you enjoy trying new things out and if you are willing to spend a weekend, you can get a working CNC machine for just some bucks. You'll get the knowledge for free. You can find the build instruction for this and even more powerful CNC machines on the project page. Thanks for watching and I'll be back.